Hello, my name is Sung Kim. I'm a PhD candidate of Electrical Engineering KAIST. My advisor is Professor Yongman. Today I'll be presenting our research progress on diagnostic interpretation in medical image. Deep learning models have achieved tremendous progresses in computer vision domains. Along with such developments of deep models, now medical diagnosis can even receive assistance from AI models. As you can see from the figure, deep models can make diagnosis of chest X-ray images and provide segmentation for ultrasonic endometrium images, giving aids for medical experts to make diagnostic decisions. This is an example of deep learning application in medical domain. A trained deep model can predict thoracic disease while given an X-ray image. However, there must be diagnostic errors even the deep model is well trained. To fully trust the AI model and make reliable interaction between human and AI models, research for explainable AI in medical domain has started. AI explainable and human interactive techniques such as visual explanation and radiology reports might be the keys for future development for AI-based medical diagnosis. One of our research for medical image diagnosis interpretation is generation of multimodal justification using visual world constraint model for explainable computer-aided diagnosis published in MICAI 2019. This research tackled a problem that medical report data make it difficult to generate an accurate sentence with large variations. Due to the lack of training set that can provide explaining sentence on the medical diagnosis, the existing deep models tend to provide duplications of sentences that the model have already seen. Hence, we designed a visual constraint word model on the top of the diagnosis network and provide the textual and visual justification for the diagnostic decision. The proposed visual word constraint model consists of diagnosis network and justification model. For the diagnosis network, any conventional cat-X networks can be utilized, thus our framework can provide interpretations on DNS decision without diagnostic performance degradation. In addition, justification model employs a visual feature and a diagnostic decision of diagnosis network. To effectively train justification model by avoiding the duplication problem, a visual word constraint loss is devised in the training stage. The figure shows the detailed architecture for the justification model. Our framework is designed to provide diagnostic analysis using lesion images and description DB being combined. And by incorporating visual features into the texture justification generator, our framework could grasp similarity in meaning with word describing same margin or shape, even without additional large word set embedding to the vector space. Here's the examples of visual and texture justification that are generated from the visual word constraint model. As you can see from the figure, we could generate textual justification that can match the margin and shape labels of given medical images with the proposed visual constraint loss. We generated texture justification that does not duplicate the sentences from the training set, but could provide variable sentences depending on the attributes of the provided images. The following research is structure boundary preserving segmentation for medical image with ambiguous boundary, which is published in CVPR 2020. The proposed work solved the ambiguity of the structure boundary in the medical image domain, considering the uncertainty of the segmented region without domain knowledge. In this work, we propose boundary key point selection algorithm to preserve boundary of the transvaginal ultrasound images while conducting segmentation tests. From such algorithm, we can provide visual explanation on which region should be preserved for segmentation. The figure is the boundary preserving segmentation framework. We first utilize boundary key point selection algorithm to automatically match ground truth segmentation region without any advising information. The proposed boundary preserving block prevents the loss of important points in boundary during encoding and decoding the input medical images. And while training the segmentation network, the shape boundary evaluation determines whether the key points preserve the important region for segmentation. The segmentation network and the evaluator are adversarially trained to generate segmentation image with well-preserved boundary key points. The boundary key point selection algorithm first randomly select endpoints for each iteration. It constructs boundary region by connecting the selected points and measure the IOU between the boundary region and the ground truth region. After repeating such procedure for several iterations, the boundary points which lead to the highest value of IOU are selected as the structure boundary key points. The selected points are utilized for preserving boundary information in the segmentation network. The proposed boundary preserving block generates boundary key points map with boundary key point map generator. The boundary key point map generator generates boundary key points map from the encoded input visual features and is optimized by minimizing the cross entropy loss between the encoded boundary key point map and the ground truth key point map. This is the experimental result of the proposed work. The proposed network preserves structure boundary of target region and visualizes the generated boundary of key points map. The results show that the tendency of the preserved boundaries are obtained with the corresponding boundary key points maps. This is the ongoing research on medical image visualization. We have done researches to solve the lack of model agnostic visualization research in medical image diagnosis domain with image perturbation. In addition, there are necessities of fine-grained visualization in medical image visualization on pixel level. We defined class distortion as a critical problem in image perturbation-based visualization methods and verified that tackling class distortion enhances the quality of explainable visualization quality. The research is meaningful that it opened the possibility for fine-grained visualization with image perturbation in medical image visualization domain. We describe class distortion from the provided figure. From the image perturbation process, manipulating images made changes to model predictions. The objective of image perturbation is to find core region of an image that purely reduces the prediction scores of the target class. However, while manipulating images, non-target prediction may be affected unintentionally, and this should be prevented. Such situation may hinder the quality of the visualization and provide less trustworthy explanations. Hence, we propose a new optimization scheme to solve class distortion problem. As you can see from the figure, unintended changes in non-target class prediction hinders the visualization quality of the medical image diagnosis. The proposed mask optimization scheme minimizes the target class prediction while preserving those of the non-target classes. In addition, we eliminated TV norm and smoothing regularization term to enable pixel-wise visualization for medical image diagnosis interpretation. The proposed mask optimization scheme does not require heuristic hyperparameter settings by cross-checking the quality of the generated mask and reverse mask. For the verification of the proposed method, we selected chest X-ray dataset. The dataset includes 14 thoracic disease classes with about 100,000 X-ray images. The backbone model is CheckSNet, and we selected 5 different baseline visualization methods. As in the figure, not considering class distortion leads to visualizing unrelated regions of medical images. However, the visualization result of the proposed method activates pixel-wise regions that are distributed in influential bounding box region. The proposed method is appropriate for medical image diagnosis that require detailed and small visualization for disease innate. And this is all we have prepared for this presentation, and thank you.